I thought I'd talk about some recent work which I did with a postdoc at Princeton called Yong Wang, and it's called Phase Transitions and Dimensional Crossover in Layered Confined Solids. The idea was to set up a system of confined two-dimensional layers confined between flat plates with a very simple uniform confinement potential, which simply kept these layers in between these two flat plates and asked the question, what are the equilibrium properties of such a system? What sort of thing one can vary is the distance between these two flat plates. And so when these two flat plates are close together, you can only get one layer of atoms in between, and if you increase the spacing between the two flat plates, you get 2 or 3 layers, and one would like to look at the structures of these atoms between the 2 layers. Okay, so I'm going a bit ahead of myself here. Now, if you just put in if you keep 2 plates close together and just have a single layer, then we all know what the structure of that single layer is. At low temperatures, it's triangular lattice, and at higher as you increase the temperature, these layers, the layer of atoms will become a fluid, and the first fluid you get is so-called hexatic phase, which has got still got a fluid with still some orientational order. Increase the spacing between the two plates, you end up with 2 layers, and so on and so forth. Now, the single layer is well understood, and then the question is what happens to when you increase the spacing so more than 1 layer. Now, the parameters of the system are the width, the separation of the 2 plates, the 2 confining plates, the temperature, and the lateral pressure, confining pressure, which makes sure the atoms don't leak out of the edges of the system. Okay, now for the single layer, one can make measurements of the top left picture is the translational 2-point function, which will decay algebraically because you can't have long-range order in 2 dimensions. So that if you increase the temperature, the translation order is exponential. Okay, but the orientational order remains, and so the middle picture is the orientational order. The top line, you have long-range orientational order. The dotted line is the algebraic decay with distance, and the green curve is the higher temperature isotropic fluid, where the orientational correlations fall off exponentially. Okay, but there are too many pictures there, so let's go to the next. Now, these are some curves of okay, so this is the evolution of the average area per atom of, for example, the two-layer triangular neon lattice during heating and cooling. And you notice that the top 2 curves, the heating and the cooling, they basically follow exactly the same curve, so there's no hysteresis. So this is a continuous transition. So that let me just conclude. This study was done purely numerically, but it sort of increases our understanding of the melting transition of these layers, which has been not understood for years and years and years. Mm-hmm. And it also shows how the two-dimensional melting problem, which is well understood, gradually crosses over into the three-dimensional melting, and how this hexatic phase, this intermediate hexatic phase, disappears as the number of layers increases. In fact, it vanishes. The hexatic phase gets narrower and narrower and eventually vanishes.
So, as you can see, I'm from the Technion, which is the first university that was established in Israel. We started teaching in 1924. The Hebrew University in Jerusalem came a year later, and these were the first universities in Israel. I studied all my degrees at the Technion. I am a material scientist, and most of my research was development of metallic alloys for applications in aerospace and aviation. And they were based on titanium, aluminum, and magnesium. While developing the right composition of titanium aluminides to be used in jet engines took 2 or 3 years, the development of the technology to produce these alloys and put a product into the jet engine took 20 years. Appreciate technology. It is not easy. It's very difficult. My tool of research was transmission electron microscope. Transmission electron microscope is a very powerful tool in crystallography, and contrast analysis of defects is done mainly by transmission electron microscopy. So it's a powerful tool if you know how to do the work on it. And not many people are real experts on electron microscopy. In one of my studies, I worked on aluminum manganese alloy, and this is where I found the quasi-periodic intermetallic compound, which brought me several prizes. So what is quasi-periodicity? Well, you know what periodicity is, like tiles on the floor, only three-dimensional, and this is how crystals were thought to be built with no exception. The science of crystallography started in 1912 by a scientist named von Laue, a German scientist, who performed the first X-ray diffraction experiment. And he started the science of crystallography. And his crystals, the crystals that he studied, were ordered, the atoms were ordered and periodic. And all the crystals that were studied from 1912 to 1982, for 70 years, all the crystals in the world that were studied were ordered and periodic. So a definition of crystal was, a crystal is a solid material in which the atoms are ordered and periodic. Very simple. And here, years later, in 1982, during my during my sabbatical at the National Bureau of Standards in Maryland, I find an alloy of aluminum manganese which is ordered, clearly ordered. It's a very sharp diffraction pattern, electron diffraction pattern, but it's not periodic. And it has forbidden symmetries in periodic systems. The rotational symmetries in periodic systems that are allowed are 2, 3, 4, and 6, no 5, and nothing beyond 6. This is true mathematically, there's no exception. And here I find an alloy that has a diffraction pattern with a rotational symmetry of 5. So it cannot be periodic, it is something else, and that was the discovery. This is part number 1. I want to tell you about something else because I have less than 2 minutes and I want to convey a message. I worked hard and many years to develop the love of science among young people. And I started 3 such programs. Program number 1, teaching science in kindergartens in my hometown in Haifa. I did it with the mayor of Haifa and his team. And we started to teach science to kindergarten children aged 5 to 6 in 60 kindergartens. It continues today. We started it in 2013, and it continues today. And it grew, and it works very well. And the municipality prepared a book of stories about science given to young children. This is project number 1. Project number 2, I thought, how can I reach large audience? How can I? Television. So I started a television program called To Be a Scientist with Professor Dan. You can find it on your laptop. If you dial To Be a Scientist with Professor Dan, you will see my lectures. There I met children age 8, not 5, 6. Last project, chronologically, the first project. At the Technion, I said, you know, our engineers and scientists will open companies. Why don't we teach them how to open a company and succeed? So I started a company, I started a course, a class called Technological Entrepreneurship. It was the largest class of the Technion, 600 students in my class, every week for 30 years. And my last words are that the Technion is leading university in the world to produce unicorns. Unicorns are private companies worth more than $1 billion. And the Technion is number 1 in producing these unicorns. So, science and technology. Thank you very much.
So I'm going to talk about neutrinos, which are one of the biggest unknowns in cosmology and also in particle physics. So neutrinos are actually everywhere around us. So starting from galaxy, Big Bang, sun, Earth, and also man-made sources like reactors, accelerators, even everybody of us. So we emit, everyone in this room, proportionate to your mass, roughly 340 million neutrinos per day. So neutrinos are fundamental. It's one kind of building blocks of matter. There are a total of 12 elementary particles, but 3 are neutrinos. So it's representing a quarter of elementary particles. You can imagine it's important. And neutrino mass in the standard model of particle physics is set to 0, but it's not 0 in the standard model of cosmology. So there's a problem there. And indeed, from the formation of the universe and the evolution of the universe, we understood that neutrino has to have a mass. Otherwise, every one of us could not exist here because there's no galaxy, no Milky Way, no sun, and no Earth. That's why the mass of neutrino is extremely important related to whether we exist in this room or not. Neutrinos can be, the mass is very small, so you can only detect at this moment using so-called neutrino oscillation mechanism, and which give you a most sensitive probe. Neutrinos can change their flavor during their flight from one type to another. For example, electron neutrinos to mu neutrinos. There's a mistake here. It's electron and mu, not M. And so there are several mysteries actually associated with these neutrinos. First, of course, we have to know the mass, and then we have to know the oscillation. And also, third one is we have to know whether neutrinos are Dirac or Majorana, which means that if the neutrinos and antineutrinos are the same particles or not. So indeed, neutrinos do oscillate. We see that in the past, 20 years ago, In 1998 and 2001, atmospheric neutrinos and solar neutrinos are discovered, and they measured the neutrino mixing parameters and also got Nobel Prize. So art is hitting in this room. And we actually measured another oscillation parameters called the θ13 in 2012 in diabase react neutrino experiment. So we see that indeed the neutrinos do oscillate, and we measure this number, and this is actually an effort by more than 250 people from 6 countries and regions, and this is actually the largest ever collaboration between China and the US in basic science. And currently, we reach the precision of about 2.8%. After the diabase experiment, we have our next experiment called the Juno experiment. They modify my slides in the wrong way, so the title is wrong. So we are actually working on the Juno experiment. And the Juno experiment, you can see that it's 60 kilometers from the reactor, not anymore 1.6 kilometers. And this experiment can measure neutrino mass hierarchy using reactors in Yangjiang, Taishan. And indeed, the Juno experiment is technologically very challenging. It has a dimension of 40 meters, and the total mass of liquid scintillator, which is a target, is about 20 kiloton. And you can imagine this is already the largest cavern, at least in China, for civil usage. And we have to build a large aquatic tank, 20 kiloton transparent scintillator, and also the phototube, which is photosensors. You see some of the pictures, and you see the size of a person. And this is actually a long journey from 2013 all the way up to this year. We started our data taking, and we managed to measure solar neutrino oscillation parameters. And this was our result just published in November last year. We measured the solar neutrino oscillation parameters, and the precision has been improved by roughly a factor of 2. So looking forward, Juno experiment will determine the mass hierarchy in the next few years, and after that, CP phase will be measured by other experiments like Hyper-K and the DUNE, and we believe that in the next 20 to 30 years, whether neutrino is Dirac or Majorana will be determined by other experiments, one of which is upgrade of the Juno experiment. Thank you.
Thank you, Rajesh. As you mentioned at the beginning, it's particularly appropriate that we're giving a talk like this because we're at the end of the celebration of the International Year of Quantum Science and Technology. In fact, we're almost exactly at the 1-year anniversary of the beginning of the celebration of this year at UNESCO in Paris. The reason I'm giving this talk is because I believe we're on at the beginning of a new revolution, like the one that started in 100 years ago. But just to review what that first quantum revolution was about, in large part, it was wave-particle duality. Einstein taught us that things like light that we thought were waves are also particles, and Louis de Broglie taught us that things that we thought were particles, like electrons, were also waves. And while this is not all there is to quantum mechanics, it's indicative of the extremely huge difference in thinking about the way we think about the world. And it led to an amazing technological revolution in addition to the scientific revolution. On the left side there, you see a picture of the first transistor, 1947, about 25 years after the beginning of quantum mechanics. To give you some idea of the way that revolution has gone, in the space of that first transistor, today you could have 10 to the 12 transistors. And that kind of revolution led to things like computers and cell phones and all the technology that is allowing us to see this, this presentation. It allowed LED lighting. This has affected essentially everyone on the face of the earth. And my point is that now we're in the midst of what some people, including myself, have called the second quantum revolution. And the nature of that second quantum revolution is multifold. One idea is ways in which we can cheat the Heisenberg uncertainty principle. You can't beat Heisenberg, but you can cheat him. And we heard from Kip Thorne one example of that, the squeezing of light that's led to amazing improvements in the efficiency of the LIGO detectors. Recent Nobel Prizes, the 2012 Nobel Prize shared by John Clauser, who's next to me, explored some of the weird things of quantum mechanics, understood by the founders of quantum mechanics, but only now beginning to be applied in technology. Superposition, the fact that something can be in two places at once. Entanglement, the fact that things can be correlated in ways that defy common sense. And another feature of this second quantum revolution is the manipulation of single quantum objects. And it's all quantum technology that's doing this. It's just technology that hasn't worked very well. If you'd asked those founders of quantum mechanics what was the what was going to come from quantum mechanics, they never would have guessed the transistor. And it may very well be that we are in the same situation, that we can't imagine the kinds of things that will come from this, this second quantum revolution. But I'm really excited about it. And one of the things that I want to say about that second quantum revolution has specifically to do with experimenting with single quantum objects. Today, we can do experiments where we make an array of atoms held in very specific positions, where we know what the state of each one of those atoms is, and where we can look at and manipulate, pick up and move around each one of those atoms. To me, this is really exciting because it means that for the first time, we as experimenters can become a Maxwell demon. We can perform the operations that Maxwell imagined in the 19th century and individually manipulate atoms. We can create artificially an essentially zero entropy system. So the kinds of studies that we can do with these new kinds of systems is, I think, beyond our imagination, and I think beyond the imagination of almost anybody. There's been a lot of hype, as has been mentioned, about quantum computing, and I think we have to be very careful not to give in to claiming that quantum computing, for example, another example of manipulating single quantum objects, we shouldn't give in to the idea of claiming that quantum computing is going to solve all of our problems. But I do expect that wonderful things are going to be done with quantum computing. And for example, today there is a quantum economic development consortium that has over 250 members from 39 different countries, led by Celia Merzbacher. And the older people in the audience will recognize the name Merzbacher. Her father was the author of that famous text on quantum mechanics. And so quantum mechanics stays in the family. And I don't know what's going to happen with quantum mechanics, but I'm really excited about it, and I'm eager to see what comes of it all. Thanks very much.